Thank you very much.
25 minutes.
And let me just thank a lot the organizers, particularly Devira for inviting me here. First time in Canada, really enjoying myself. So my group in Dublin, I would say works on two principal topics. The first one is sort of non-equilibrium thermodynamics of quantum systems, and the second would be like more traditional many-body physics, and sometimes those two areas intersect. And today's talk is going to be on the thermodynamics side. So I'm going to talk about something called Mpemba effect, which was mentioned previously in Ronnie Koslov's talk for those of you who were there on Tuesday. So yeah, it's based on a recent-ish work. It's currently with the editors. Let's hope that they get back to us soon. And the people involved are shown here. The leading author is Mpemba. So Matteo has just actually handed in his PhD thesis in Munich in the group of Uli Schalwak, and he'll come to my group in Dublin as a postdoc in October. Chrisia has recently left as her postdoc position in my group and moved back to where she's from in Brazil, take up a position. And Oshin Kolan is my PhD student who's actually just finishing up his PhD thesis at the moment. I took the email I got from the organizers pretty seriously when they asked to kind of do a very kind of broad and gentle introduction to the area. And I understand that although there are some experts here and looking at them, some of them now in quantum thermodynamics, this is not kind of reflective of the main audience. So I'll try to be fairly simple, and apologies to the experts for over-trivializing perhaps. So I'm going to talk a little bit about the history and background of this effect, something about kind of open quantum systems and thermodynamics, and then I will sort of give you my take on this thing, which is becoming popular despite its very kind of old nature, show you some results, and then actually, probably more importantly, give you my take on some nice directions moving forward, because it's quite a simple idea. It actually originated from a journal club. We just did it for fun, but actually it's got me thinking about some problems which I find a little bit more general, and I can tell you about some of them. Okay, so if you Google the Mpemba effect, you're going to find crazy photographs like this of Russians and Canadians and people who live in cold places dangerously firing hot boiling water pots over their heads and making these spectacular images. We could add to these images if Ronnie has a photograph of him putting his grandson's popsicle into liquid nitrogen, like he said in his talk for his school project, but I'm not sure if he took the photograph. So the idea of hot water being able to freeze faster than cold water is actually about 2,000 years old and was first mentioned actually by Aristotle. You can find in his writings this observation. There was a group of Greeks that lived high in the mountains, and they made fishing rods out of reeds, and to get the reeds to stiffen, they would immerse them in boiling water and wait, okay, to stiffen the rods. So you see in his writings, he discusses this effect. And then it was kind of mentioned by a bunch of people throughout the history, like Descartes and Bacon. So you see this quote by Descartes, so water that has been kept on a fire for a long time freezes faster than water, without any general explanation. And I guess the first, the effect that the name comes from is from a person from Tanzania called Erasto Mpemba, that's shown here. So here he is outside the Royal Society of Chemistry in London a few years ago. The Royal Society of Chemistry in London, they offered a prize for people who could actually make some sort of theoretical description of why this Mpemba effect occurs, okay? So the story is kind of folklore at this point. He was a student in Tanzania in the 60s, and they were making ice cream in home economics class. And when you make ice cream, you have to pasteurize this, or heat up this milk and sugar solution, typically wait for it to cool, and you put it into the freezer, okay? So he was in a hurry, and he put it into the freezer when it was hot, and he was surprised to find out that his solution had frozen quicker than his classmates, okay, who had put it in when it was cool. And, you know, he said it to the teacher, and the teacher said, no, this is nonsense. You know, this violates Newton's law of cooling. You should know your physics better. And about a year later, a physicist called Osborne, who was he was working in the University of Dar es Salaam, came along, and Mpemba mentioned this to me. He said, look, I don't think it's true, but I'll try it anyway, okay? So they did this really crude measurements on the freezing of water. So what you see up here is actually from a paper that they published in 1969 called Cool. By the way, which is a really great title of a paper. And it's cited very many times at this point, right? So you see, they show the time for kind of freezing versus the initial temperature. And you see this non-monotonic behavior of the curve, which is, okay, look, it's a bit rudimentary, but it was improved on, and people debated for many years, since 1969, as whether it actually was a real thing or not. And more recently, if you look in the literature, you'll see this actually an explosion of work being done, in particular in the statistical mechanics community, observing similar effects, not necessarily in systems which have boiling and freezing points, but generally this observation of the anomalous effect whereby essentially, cold things, hot things freeze faster than cold things. And more recently, again, you'll see 2,000 years after Aristotle, PRL in July has like, kind of a triple highlight of 3 different type of Mpemba effects in quantum systems. So let me just explain to you, because there's a bit of sort of diversity in the different types of effects. They have this schematic here of classical open system, closed systems. I can argue later that actually they're all manifestations of the same underlying physics, but the closed system case is a very different phenomenon. So this is studied a lot in the group of Pasquale Calabresi and Trieste in Italy. So what they actually do there is they have many-body systems which are U1 symmetric. So say, for example, they conserve magnetization. And of course, if you have a low-dimensional system in 1D, you can't break a continuous symmetry. But what you can do is you can start off with an initial condition, like a tilted antiferromagnetic magnet or something like this, which essentially breaks that U1 symmetry. And then under time evolution, yeah, the system restores that symmetry, okay? And so what they observe is that states, okay, which initially have more symmetry breaking, okay, relax their symmetry restored state quicker, okay? But in the end, if you think about thermalization, it's actually time translational symmetry restoration. So it's just a different basis. So this is all sort of manifestations of symmetry restoration effects. And this has been now tested in a number of experiments. So you see an experiment here in sort of quantum simulators, so the programmable digital simulators. This is like you see people like Rainer Blatt, Peter Zoller, people that are very prominent in that community. And in a single trapped ion experiment done in Israel by some of the kind of founders of this area. So why did all of this stuff reemerge again as an interesting topic, right? And that was the following observation, okay, that in classical stochastic thermodynamics, okay, in 2017, there was a group from Weizmann, okay, which have at least understood the effect mathematically in a very important class of systems, which are continuous time discrete state Markov processes, which are one of the working horses of, for those who know, one of the working horses of the theory of stochastic thermodynamics that I'm quite fond of. So the idea is that you have, you can think about some system, that system is open, it has some sort of metastable landscape, so it has some sort of energy landscape. It looks like this, where you have activation barriers, you have tunnelings, you have energies, the usual story. And obviously, to solve such a system is very easy. This system has detailed balance. You construct the rate matrix so that it drives every probability vector into a thermal Boltzmann distributed vector. Yeah, it's really what we do a lot in stochastic thermodynamics by looking at thermodynamics along the trajectories of such a stochastic system. Okay, so it's very kind of rudimentary idea. And what these people did, which was very nice, was they started to try to understand what was going on when they started with probability vectors which were at a different temperature to the fixed point. Okay, so for example, if you look in the simplex of all possible probability distributions, you see this red-blue curve is the quasi-static locus. So this is the locus of probability distributions, which are all thermal. But of course, you're free to choose whatever initial condition that you like, right? And they sort of define the Mpemba effect as the following. Consider some distance measure on the space of probability distributions, whatever your favorite distance measure is. It could also be a distinguishability measure like Kullback-Leibniz divergence, something like this. And you have 3 temperatures, right? You have the temperature of the hot initial condition, the temperature of the cold initial condition, and the temperature of the fixed point in which you're being driven to, okay? And all states, all initial states will eventually relax to the fixed point trivially under such a situation. And the Mpemba effect exists okay, if at some time, say Tm, Mpemba time, the distance between the hot evolution and the fixed point is less than the distance between the cold evolution and the fixed point, okay, in probability space, for all times greater than Tm, okay? And you know, what you can always do with the Markovian system or in general, okay, is you can take the rate matrix and you can expand out the probability vector in terms of the left eigenvectors of the rate matrix. So you have pi Tb is the thermal fixed point, and you have a bunch of decay modes, okay? And those decay modes speed essentially is dictated by the eigenvalues of those corresponding left eigenvectors. And what's important is that also what's involved is the overlaps between the initial state and those left eigenvectors, okay? So what they kind of, which seems intuitive in hindsight, is that I should also mention that if you have detailed balance in a Kaskala system, you're going to have real eigenvalues, which is important. In the long time limit, okay, the probability vector's evolution is dominated by the slowest decaying mode, right? So the time scale, the asymptotic time scale to reach equilibrium is the inverse of the spectral gap of the rate matrix, okay? And you can see that if your initial condition, okay, forms cancellation with the slowest decaying mode, then you can have a situation, for example, where the modulus of the overlap in the cold case is greater than that in the hot case. And in that case, you can see essentially this Mpemba effect. So they understood at least mathematically in Markov processes, and even in a later work, they pointed out there are certain situations where you can get complete cancellation, and then your hot evolution is exponentially faster to reach its fixed point, because of course it's now dictated by lambda 3 rather than lambda 2, the inverse of lambda 3. Okay, so this was actually verified in an experimental system here in Canada, actually in Vancouver, in a colloidal system where they can construct kind of arbitrary energy landscapes. And the nice thing about those type of experiments is essentially they can measure kind of trajectory quantities, right? So they have very good kind of control over that. And what you see here is they can also sort of post-select, if you want classically, different distributions. And you see up on the right-hand side, you see that the hot sample was reaching this sort of thermal equilibrium faster than the cold one, okay? In fact, they were able to even show that sometimes they get exponential faster cooling just by sort of choosing the right initial condition. So this was very nice work that also, in a kind of subsequent work, showed an inverse Mpemba effect, right, which is the opposite way around. So we are quantum people. So now we want to think about this and how this generalizes to sort of quantum Markov processes. And it's not that different, actually. The main difference is even is basically that you're allowed to have sort of coherences in your density matrix as opposed to evolving a probability density, okay? So this is the standard Lindblad master equation. You see it consists of a unitary part and a dissipative part. And the generator, of course, has got, it's not a unit, or sorry, it's not Hermitian, but it's Hermitian preserving. So essentially, you have, generically speaking, you're going to have an eigenspectrum which occurs in complex conjugate pairs, okay? So the steady state, again, is the lambda equal to 0. Spectral gap is defined as the inverse, sorry, the real part of the lambda 2, and this is basically the starting point, okay? So we kind of looked at this, and you can do exactly the same sort of expansion as they do classically in the right eigenmatrices of the Liouvillean. Okay, so this is Liouvillean is a super operator, so you can make such an expansion. And as I said, the time scale asymptotically to reach equilibrium is the inverse of the modulus of lambda 2. Okay, in an open system, always, right? So, you know, so we were looking at this paper, which is very nice, in E.R. Livanovsky's group, okay, which asked a very nice question. They were like, okay, if I have a density matrix, okay, which undergoes dissipative evolution under any given master equation that's Lindbladian, okay, can I find a unitary on that initial state such that I always get an exponential speed up towards the fixed point? Okay, this is what they did. And the point is that you can, so what that means essentially is that you want to find that the Hilbert-Schmidt inner product that appears as the overlap that goes to 0, okay? And then you're dictated by lambda 3, okay? Timescale is inverse lambda 3. So they found such a unitary, but under restrictive settings. So they have no, they had no conditions on the type of Lindbladian it was. They wouldn't require detailed balance or anything like that. But they have some assumptions on how they construct U mathematically, which I don't want to get into. For one, what was restricted is they restricted to initial pure states. Okay, their proof relied on this. And secondly, which again is restrictive, that the spectral gap is defined by a real eigenvalue. And of course, those of you who work in open systems know that there is no reason why your spectral gap has to be defined by a purely real eigenvalue, okay? It's usually just a real part of a complex conjugate pair, okay? Generally speaking. And it doesn't seem so easy to construct such a U to get rid of these things simultaneously, okay? That's what they point out. So that was our starting point. And what we wanted to do in this work was to actually take one step back in generality in the class of master equations and require quantum detail balance on top, just like the Lewin Raz case, the classical case. So we really want our master equation to drive initial density matrices to thermal states. And this is rigorously described in open systems theory under something called the Davies generator. It was studied a lot in the 60s and 70s. It's very instrumental in the field of quantum thermodynamics. And this structurally, what you see for a Davies generator and how you define detailed balance in general for an open system, which was actually first done by mathematical physicists. For example, Robert Ilishky has really defined detailed balance for open systems. Mathematically, what you do is you impose that the dissipator is Hermitian under an inner product, which is called the KMS inner product, right? So this funny inner product over here, which becomes the standard Hilbert-Schmidt inner product in the limit of infinite temperature, the one that we all know, okay? So this has some structural consequences if you go through it, right, on the mathematical structure of the Liouvillean. First of all, and again, it's very obvious for open systems people, the unitary part and the dissipative part commute, and they share, therefore, a common eigenspace, which are the outer products onto the energy eigenstates of the Hamiltonian, okay? Furthermore, and what's more importantly, if you view the full Liouvillean, okay, as a sort of matrix, you can always kind of write it as a matrix, provided the Hamiltonian, it doesn't have degeneracies, the generator factorizes into subblocks, right? So you have a subblock which describes the evolution of populations. So therefore, if I start with a density matrix which is diagonal in the energy eigenbases of the Hamiltonian, it remains in that subblock. And likewise, you have a larger coherent subblock. Okay, so this describes the decay of coherences. This is sort of bread and butter for open systems people, but again, if you're not from that community, maybe you don't know it, so fine. The other thing is that you can find out that the left eigenmatrices, okay, left eigenmatrices of the Liouvillean, they correspond to populations, okay, and they're diagonal in the energy eigenbasis, right? So they have purely real eigenvalues, whereas the left eigenmatrices, these correspond to coherences, and they're pure off-diagonal in the energy eigenbasis, basically where the eigenvalues come in a complex conjugate pair, okay? So this is like structural stuff that comes from this Davies generator stuff. And that's sort of what we wanted to do. So again, this is sort of just the first finding. So trivially, you can always find a unitary now on an initial state, which will basically delete those modes, right? And it's basically any transformation that brings your initial state to be diagonal in the energy eigenbases of the Hamiltonian that will kill all the overlaps with those modes which come in complex conjugate pairs, okay? So, now the thermalization rate is defined by the first real eigenvalue, okay? You may not have a complex conjugate pair as your first set of eigenvalues, okay? But if you do, you'll always get an exponential speed up. The question now you ask yourself, is this a Mpemba effect? Where is temperature, okay, in this? So this is the next thing. This is where sort of quantum thermodynamics reasoning comes in, okay? So that's just a takeaway. If I find a transformation which brings my state to be diagonal, if I have a spectral gap defined by a complex eigenpair, I will get an exponential speed up towards my fixed point. This is true under Davies generator. So a nice thing that you can do now, okay, is you can exploit the concept of non-equilibrium free energy, which we use a lot in thermodynamics. And actually, for me, it's one of the most important things in quantum thermodynamics, which is you do the following. I take the energy of any density matrix, okay, and if it's undergoing evolution towards a thermal fixed point, I can always write it as this, right? Because I can take the log of an exponential, right? It's just a kind of triviality. I just play some games, I manipulate the expression, and what I find is an expression which is basically looks like this. So the internal energy is equal to the quantum relative entropy between my time evolving state and my thermal fixed point times the entropy of the time evolving state. So what you do is you just bring the entropy across over the other side. You've got a free energy, which is you've relaxed the assumption of equilibrium states, and you get this so-called non-equilibrium free energy, which is this Kullback-Leibniz divergence or quantum relative entropy between your time evolving state and the fixed point and the standard equilibrium free energy, right? So if I am in equilibrium, it's just a free energy, okay? And if I'm out of equilibrium, I have an additional contribution, which is the relative entropy. And the first place I've seen this in literature was 1987, old paper by Matt Donald, but maybe Ronnie can tell me there's something else, I don't know. Anyway, the nice thing about that, for those who know again about thermodynamics and open systems, is that the time derivative of it is the famous Schwann-Lebowitz formula for the entropy production, okay? But that's just a technical thing. So the relative entropy has some nice properties, the quantum relative entropy. For example, it's always positive, okay, by Klein's inequality. It's not a distance in itself, okay, because it's not symmetric. It doesn't obey triangle inequality, but it is bounding, sort of distances. But most importantly for this Mpemba stuff, you have data processing inequality. So it means it's monotonically basically decreasing under completely positive and trace preserving evolution, which means that you have this kind of hierarchy, right? And that's very important. Now we want to apply this to understand our kind of effect, right? Okay, so that's sort of this is. And as I said, the other thing which is very important about non-equilibrium free energy, and you'll see this in a very nice review on entropy production by Gabriel, actually, in RevMod Phys, is that, what's customary in non-equilibrium thermodynamics is to make a kind of ad hoc division of the rate of von Neumann entropy change with respect to time into the irreversible entropy reduction minus the flux, okay? The flux is the heating rate, right? So if I'm in a non-equilibrium steady state, the SDT is 0, my entropy production is the heating rate, okay? But this is kind of standard irreversible thermodynamics division to do. And you can note here that, as I said, if you take a derivative, so the equilibrium free energy is time independent, if I take a derivative with respect to time, I get the following, which is minus the derivative of the non-equilibrium free energy, so the relative entropy. This is a very famous paper by Herbert Spahn in the 70s, which shows that in continuous time semigroups, the entropy production rate is given by the derivative of the relative entropy. Okay, this is a super famous result. And the other thing that's kind of nice, especially for the effect that we want to talk about, is something that was done kind of more or less the same way in our group and also with Gabriel's group, is that you can take the quantum relative entropy and you can make a nice splitting if you have a Davies generator, which means you can split it into a part which comes solely from populations, and you can actually split it into a part which is the quantum relative entropy of coherence, which is formally speaking a coherence measure in quantum information, right? So this is kind of a nice thing. And now we're kind of in the sort of, I want to skip this slide. Now we're in the sort of position to define what I would say is the analogous quantum Mpemba effect, right? So you take 3 states now. I've got rid of the notion of temperature and I've replaced that with the hierarchy of non-equilibrium free energy, right? So I have an initial state, can be whatever. I have some state that I've transformed, rho prime, okay? It doesn't actually have to be unitary, but for the purpose of this talk, let's say it's unitary. And I have a fixed point, tau beta, okay? Now, the non-equilibrium free energies, because of the data processing inequality, okay, means that the rotated state will always have a greater non-equilibrium. You can always construct a unitary on your initial state such that your new state will have a higher non-equilibrium free energy than the previous one. And that's, you can think about this the following way. Think about a unitary which rotates the energy eigenbasis and flips the eigenvalues around to a population inversion. This will have a bigger non-equilibrium free energy than any other state. And the Mpemba exists if there exists some time such that the non-equilibrium free energy of the a rotated state, okay, is less than the non-equilibrium free energy of the non-rotated state for all times greater than Tm, okay? And the key finding of our work is that if the generator has a spectral gap defined by a complex eigenpair, then a unitary or a generic transformation actually can always be found, okay, such that an exponential speed up and a genuine quantum Mpemba effect occurs, okay? So you know, you can sort of sort of play some simple examples. Of course, if you're a theorist, the first thing you do is you look at a qubit undergoing a kind of Davies evolution. So if you look up here on the right-hand side, you see the green dot is essentially, you know, the state with coherences, and you see that the red guy is the initial state, and obviously under Davies evolution, you have to traverse the Bloch sphere in a greater length to get down to that fixed point which lies on the pole. Okay, so it's kind of easy enough to see there, and here you see the plot of the non-equilibrium free energy versus time for the two different states, and you see this crossing. Okay, this is the signature of Mpemba, right? So your two initial states which break time translational symmetry. Time translation symmetry is being restored by the thermalization process, and there exists some time Tm where these curves cross, is a sort of Mpemba effect. And just to show it's not just a triviality, we also did numerical calculations on sort of less trivial models like the transverse easing model. And although the effect doesn't appear to be universal, it's certainly ubiquitous. Okay, you see it all over the place if you start looking for it. Okay, so that's sort of the main contribution of that work. And as I was saying, it's kind of cute and it's a nice idea, but it got me thinking about a number of different problems which I find of more general nature. Okay, so I want to just quickly shift the gears and tell you about something that I've been thinking about in connection to this. So you can see somewhere from this Bloch sphere picture in the case of qubit, there is some geometrical feature to this, okay? Even though it's very difficult to think beyond the Bloch sphere for more generic problems. There's been a lot of interest in the classical stochastic thermodynamics community recently. So I spent July in Japan, in Kyoto, and you know, if Nicole said that thermodynamics is a British subject, then the application of information geometry to thermodynamics is definitely a Japanese subject. So the idea here is actually very much connected to the notion of Fisher information that we know and love from metrology. And often as physicists, we're just really taught about Fisher information from the perspective of parameter estimation, but actually Fisher information is also a generic geometrical thing, okay? So what people have recently started to do is kind of connect this idea of information geometry, which is the study of probability distributions, multi-parameter probability distributions, okay? So you think about, you know, the set of, you think about one parameter, for example, you vary, you get a probability distribution in the parameter space, and then you ask sort of questions about the geometry that induces, okay? So what's central to this field of information geometry is the idea of the Fisher information forming a metric on the space of probability distributions, okay? So if you think about this object here, okay, which is called the Fisher information metric, its diagonal elements represent the amount of information that observable random variable provides about a parameter, which is why it's connected to parameter estimation. And what people in this stochastic thermodynamics community have started to do relatively recently, okay, is to consider the parameter to be time itself. So I just want to explain a little about that. So as I said, in the space of probability distributions, okay, which have some parameter theta, you can, the Fisher information matrix forms a metric. Therefore, you have a squared line element, which is defined like this, okay? And this gives a statistical measure of distance over the manifold of probability distributions. That manifold is Riemannian. You have all of the nice sort of properties of Riemannian metrics, okay? Again, it's well known. So one way to think about what the Fisher information is, think now you have two probability distributions at parameter, single parameter theta and theta plus delta theta, and I want to understand the distinguishability between those two probability distributions. So what you do is you take the Kullback-Leibler divergence, you perform a Taylor expansion, okay, and you see basically the leading term is the Fisher information. So it tells you something about distinguishability of probability distributions. Something then that's cool that you can do is you can define a length, okay? A length, because you have a metric, you can define a length. So if you want ds squared is square root of Fisher information. Square root of Fisher information is kind of like a velocity in the parameter space. And then if you integrate that over the path, okay, you get a length, because as you integrate a velocity over the path. So now what's next is that you'd like to be able to sort of choose your parameter. And this is work that I'm doing with my student Letizia, who's here actually. She's doing great stuff. We should nearly finish, but anyway, is think about this in the space of density matrices, okay, that are evolving in time, okay? So time now is the parameter that enters, okay? So one thing that I sort of learned only recently, which is very, very interesting, is classically, if you have probability distributions, the Fisher information is the uniquely contractive metric on the space of probability distributions, right, under stochastic maps, which means you can't increase Fisher information by applying noise, right? That doesn't make sense. You can't increase distinguishability by applying noise. Quantum mechanically, in the 90s, when people were interested in the geometry of quantum states, Petz showed that actually this uniqueness is not there, and there's a whole continuous family of different quantum Fisher informations, which is basically stemming from the non-commutativity of density matrices in quantum mechanics. So this is known to people in kind of mathematical quantum information. And if you actually go through the calculation and you say, okay, I have some single parameter density matrix, I can write it in an instantaneous diagonal basis in the theta space. If I do the calculation of this line element, you see that you get a term, which is the classical Fisher information on the diagonal matrix elements, but due to the non-commutativity of rho of theta and the derivative of rho of theta with respect to theta, you get this sort of off-diagonal contribution, right? Which can stem from coherences. And this thing, okay, if you want a particular metric, you have to expand different divergences. For example, if you expand the quantum relative entropy like you do in the classic case, you will not get the SLD Fisher information that we know from metrology. You'll get something called the Kubo-Mori-Bogolov form, right? So if you want to get the one that you know from metrology, this SLD, you have to expand like Burr's fidelity, right? Something like this. So there's a whole garden of different quantum Fisher informations which come from different divergences. Okay, metrology, SLD, relative entropy, KMB, this is Vignari-Nassi, which is another one, okay? So all of this type of thing. I'm nearly finished. So I just want to make the following point that now you have the ability again to define the length because you have a Riemannian metric, you choose the metric, and there'll always be a contribution in the length from this coherence part, okay? From the ability of the density matrix to not commute with itself at different times, different theta's, okay? You know, this sort of tightest one, so the smallest quantum Fisher information is always given by the SLD, which is good for metrology because it means it gives the tightest bound terms Kramer Rao. But you can play lots of games stemming from this geometrical structure and trying to find the link with thermodynamics, which I don't want to really get into now. We're kind of writing about it, but in the context of Mpemba, if you leave time as a parameter, what's kind of useful is that you see that this length becomes an integral over the process time of the velocity of the state in state space, okay? So this defines a statistical length, and now you can use that to try to understand various different anomalous thermodynamic processes. And yeah, so you can define, for example, something called degree of completion, and the degree of completion is basically you take the statistical length defined up to time t, and you divide by the total length of the process. So you have some number between 0 and 1, which tells you how much of the process has been completed and things like this. So it's useful to understand anomalous thermodynamic processes. I don't want to say too much because we're out of time, but of course, the statistical length is bounded from below by the geodesic. Okay, so and the geodesic can be computed for certain metrics, and that's very interesting for certain purposes. So what you see on the left here is basically you see that the coherent state, the non-rotated state, the one that's slower, has a larger length, okay, but its geodesic is actually quite small because you don't go through the Bloch sphere, you have to go around it. And then the rotated state actually follows its geodesic path. Okay, this is a sort of observation computed with the SLD form. And then I have lots of things to say about this. For example, you can also get nice bounds and observables, which are like generalized Mandelstam bounds. This has been discovered recently using the same approach. So you can connect with things like heat currents, etc. But I don't have time to get into it. So that's kind of what I wanted to say. Just to summarize, if the generator has a spectral gap defined by a complex eigenpair, then a unitary or a transformation can always be found such that an exponential speedup and a genuine Mpemba effect occurs in a quantum system, in very simple systems and in very complicated systems. It's quite ubiquitous. In my mind, as far as I can see, we're kind of the closest in spirit to the Lou and Raz original work, because we're literally using a master equation with detailed balance, except we're allowing for coherences in our initial state. You know, you might ask the question, does this allow for some novel cooling schemes? I had kind of some dissipative quantum computing in mind, where you may do some transformation on the initial state and just allow it to relax, and you get faster relaxation is always good. I'm thinking about this problem that I was talking to Ronnie about during the week of transitions between non-equilibrium steady states that may be a little bit different. But most importantly, I think that this information geometry approach, which is what we're working on, gives a very kind of broad framework to understand all of these different Mpemba effects, classical, quantum, closed, open system effects, because the Fisher information is actually, for those who know, this is something I've been talking with Iman Marvian, who's now in Duke, because he's really expert in asymmetry. So the Fisher information is actually an asymmetry monotone as well, okay? So it measures how asymmetric you are with respect to some basis, in the case of thermalization, the energy eigenbasis, okay? So I think where we're going is trying to use that approach to kind of see if we can understand all of them under one setting, okay? That's basically all I've got to say. Inspired by ice cream. And yeah, so that's the group in our group retreat in Aran Islands. Thank you very much.